All right. So today we're going to be talking about renormalization of local operators and critical exponents. I think actually I'll probably focus more on solving the Callan-Symanzik, but we'll see. So what did we discuss last time? We talked about the Callan-Symanzik equation. The Callan-Symanzik equation, to just recall what the process was, recall what we did in renormalized perturbation theory. We took the bare fields and wrote and introduce a bunch of renormalization wave function normalization, z of phi to the power of half or phi of r. Of course, phi of r will be mass dependent, z will be mass dependent, renormalization scale dependent, but phi naught is not, right? So there's some arbitrariness in this splitting, and that arbitrariness is fixed later on by renormalization conditions. So L is the Lagrangian of the free fields and not free, bare fields and bare couplings. We write it as a Lagrangian density of the renormalized couplings and renormalized fields plus the rest that we call counter terms. Then we had then we treat this as these counter terms as terms in Feynman interactions, right? So they would contribute, they will have their own Feynman diagrams, and these are treated del z, del lambda, and phi r. Del z, del lambda are treated as well. They'll contribute. They're treated as couplings in a sense, in a sense. All right. So the renormalization condition is what fixes the relation between these, and the way it works is that, for example, if you want to renormalize some sort of a phi 4 theory, you pick an observed value for the 4-point function at a certain scale. The scale is, and then you match it to the observed value, I lambda renormalized, right? So this will fix for you the relation between deltas and m, right? So everything, all the m dependence will go in here. All right. All the m dependence will go into the wave function normalization, the counter term for the wave function normalization, and the counter term for lambdas. So that's what we did for in renormalized perturbation theory. In RG flow, there's a second step. So now that you normalize your theory, then you say, let's change the renormalization scale from m to bn. B is a constant less than 1. Then the couplings will have to change as well, right? So we're changing m on this side. The couplings will change as well, and so will basically all the renormalization, the wave function renormalizations. Call the endpoint connected correlator at renormalize some physical mass m with some renormalized couplings lambda r. This is the called gn. All right. So here is the relation. Consider the endpoint function of the bare fields with the bare couplings, in the bare theory with the bare couplings. This, we're going to write it as the endpoint function of the renormalized fields. Of course, the renormalized fields with the bare fields, they're different by this z and m, because there are n of them, and then we introduce z half as the difference, so you get z to the power of n over 2. And then for this equation to hold, this is m dependent, so this side better be m dependent. It could depend explicitly on m, or it could depend on the m through its couplings, right? All right. So of course this side doesn't see m, so if you shift m, if you change m, this side will not change, which means that this side will have to change by 0. The net change will be 0. And under shift in delta m, so m goes to m plus delta m, the couplings, the renormalized couplings will change this way, and the wave function normalization will change this way. This is the renormalized correlator. D of gn will have to be n del eta, right? Because the variation of this term will have to cancel the variation of this term. So this is these two sides. Now, the variation of this will come from two parts: the explicit dependence on M, and then its dependence on M through lambda, right? So now we call M del lambda the beta function, dependence of the coupling on scale. And we call gamma as del eta del lambda, del eta del M times M with a minus sign. This is the dependence of the field on the scaling scale M. Good. The Callan-Symanzik equation is a statement that this guy is M independent. So if you vary it, you're going to get M del M plus beta del lambda plus N gamma of the endpoint renormalized correlator is equal to 0. Good. Now, this was the Callan-Symanzik equation. Then we took the Callan-Symanzik equation and tried to evaluate it in renormalized perturbation theory for lambda phi 4, and more generally for some theory with a massless mode with a renormalizable action with some sort of vertex of G2 power of N. And then we saw schematically how it will look like. We saw that the beta functions, we could explicitly solve for them at one loop, and it took the following form. Beta of lambda became M del M of minus the counter term for the corresponding coupling plus half lambda sum over del zi's, right? This came from there were two steps in this derivation, if you recall. One was the statement that the only M dependence and came from the counter terms. All the M dependence went there. And then there was some sort of expansion we did for G2 and Gn, and we saw that the structure is true. Now, applied to QED, for example, it tells you that, well, there's delta 1, delta 2, delta 3, and this is the relation between them, right? These are the beta functions. Then we plugged in the value of these deltas because we had, we renormalized QED at one loop, so we knew the value of these guys. We plugged them in, and we found, interestingly, that the beta functions for E were positive, which means that the coupling of electron with photon grows in the UV. That is problematic, right? The theory is in the UV is, well, as a matter of fact, we'll see later in a couple of lectures that if you plot the coupling of QED as a function of scale, so it's growing, right? It will actually, at some finite energy scale, it will blow up. That's called a Landau pole. So this theory, when we say the theory doesn't exist, it means that, well, it blows up at somewhere. But remember that can't be because, well, for many reasons. This calculation is one loop, so it's not so trusted. As it grows, we need to take into account all the other things. But there's no indication of beta turning around and becoming negative due to non-perturbative effects, right? So this theory, we say it doesn't exist. We can't establish that it exists, right? That's QED. All right. Good. Any questions?
QED doesn't exist.
As an EFT, it exists. As an effective field theory. But not as a UV complete sensible theory. Even up to the physicist standards. All right. Questions? Pure QED, right? Massless pure QED. Sorry, I should call it pure. Massless QED. Any questions? All right. We talked about beta function and scale dependence of couplings. And we said that, well, we have the theory that is Gaussian, sorry, the theory that is scale independent, right? The trivial fixed point, that is say massless, for example, it's a CFD, right? The trivial fixed point could be a bunch of massless modes. Massless scalar field theory, for example, is an example of that. So we think of quantum field theory as a deformation of fixed point by some operator that is relevant, which means that this way of viewing it is that your CFD sits deep in the UV. You make a relevant deformation that grows in the infrared, and then you're the infrared observer. You see a non-trivial theory, right? That is the modern perspective for what it means for the theory to exist, right? Now, if you found the beta functions of your coupling to be positive, that means that this picture, this story that you just told, does not quite hold. It has to be something more complicated, right? Okay, good. So now every theory, the way that we discussed, we're discussing quantum field theory, the Lagrangian approach to quantum field theory. So we organize our operators in terms of derivative expansion and the field expansion. So there's always a second order term in the field with no derivatives that we call the mass term, right? So that mass term, obviously by dimension counting, above 1 + 1 dimensions is always relevant for a scalar, right? That should be obvious, right? Why is that? What's the coupling of the mass term?
Hey, what do you mean?
What is the coupling for the mass term? What is the vertex? It's a line.
It's a line, yeah.
Okay, so what's this coupling? 5, 5. It's m squared is the coupling. What is the dimensionality of m squared? It has positive mass dimension. By the way we introduce, like relevant, the very definition of relevant, irrelevant, we said that all the modes that have positive, all the couplings with positive dimension are relevant, right? So it is always relevant, which means it grows in the infrared and it can never be neglected, right? So what we're gonna do is so as it grows, it will. Another thing, if the theory is purely the massive free fields, no other thing is turned on, that theory is exactly solvable. We solved that. That's a Klein-Gordon theory. Why is it solvable? Because it's Gaussian. Still remains Gaussian, it's solvable. But the moment you turn on other terms, there will be all sorts of mixing. As we saw, the effect of higher terms will renormalize the mass, and then the mass will change the coupling so that the theory gets complicated. So what we're going to do is we're not going to pick a large mass and make a small coupling deformation. We're going to treat mass also as a small parameter, right? We're going to treat it as any other term. So in particular, m squared would be treated as a coupling. So there will be a beta function for it, but we write it as gamma of m, not to be confused with this guy, right? So what it is, well, it's del m squared, right? Of gamma of m. This is the way that the definition works. So you could just treat it as if it's coupling. Questions? Now, there's something special about this. In the previous lecture, in our discussion of beta functions, I focused a lot on renormalizable terms. We talked about couplings that were renormalizable. Those couplings, by naive dimension counting, have dimension 0, right? So when the gammas that we included for such guys, we called it the anomalous dimension, because the classical dimension, let me not jump ahead. I didn't quite call it the anomalous dimension yet. I'm going to explain that today, right? What we're going to do today is we're going to repeat the same thing. Actually, I'm kind of going through this really fast. We're going to introduce some generic operator. This could be 5 squared, 5, 4, some whatever, right? And this will be the associated coupling. And all I need to care about is that to keep track of is the dimensionality of these guys, right? And then we're going to write down the Callan-Symanzik for the endpoint functions. Good. It could be mass, it could be 5, 4, it doesn't matter. And then this is the story of renormalization of a local operator. That is half of the title of this lecture. The other half of the title of the lecture is that, well, if your fundamental field is phi, what other local operators do you know? Phi to the power of n with a bunch of derivatives, for instance. How do you make sense of such an operator? Those are composite operators. Do you know how to make sense of phi squared, phi cubed, phi 4 as an operator?
Phi applied to phi fits.
There's a problem with it. Remember when we drew the Feynman diagrams? When we did the Feynman diagrams, we did the Feynman diagram real space as well, right? And then phi squared, it looks like they're sitting on top of each other. Phi 4 term that we had these divergences. The phi squared could be viewed as, let's say, well, this is supposedly going to be phi squared. Okay, if it is an operator, let's calculate this 1-point function in the vacuum. What do you obtain? It blows up, right? What is in a free theory? What is this? A massless free theory. Actually, do you know what this is? E to the power of 2 to the power of b minus 2 over 2, right? So it blows up. How do you make sense of this in a free theory?
By multiplying distributions.
No. You know the answer to this. You've seen it. We did this in detail last time.
Reading a particle at that point and destroying immediately.
No. So this has a divergence. What you want to do is you want to define this operator, and the 1 point, if you want the resulting operator, you're going to call phi 2 of x. You would like the 1 point, imagine you would like the 1-point function of that in the vacuum to be 0. How would you do that? You would take this guy, subtract from it this.
Normal ordering.
This is normal ordering. This is a normal ordering for 2-point function. Normal ordering was precisely invented to make sense of, we never wrote phi squared, we wrote this guy. This is an operator. Phi squared of x is not an operator. Why? It's 1-point function, 2-point function, everything blows up. It's not an operator, right? Or said differently, phi squared of x, to make sure something is a good operator, one way of making sure is that you act with it on the vacuum and see if you get a vector in the Hilbert space. If you act with this guy on the vacuum, what vector do you get in the Hilbert space? It's not in the Hilbert space. It has infinite norms. As a matter of fact, phi x is not an operator either, because its norm is phi squared. But anyway. All right, so in summary, that was a detour. Today we're going to talk about local renormalization of local operators and composite operators, because local operators in Lagrangian and quantum field theory, we make sense of them in terms of composite operators, right? How to make sense of this. You already know the answer. It's through some version of normal ordering. You should also recall that there are various orderings we could do in free field theory. I discussed at least 2, but anyway. Questions? The other thing that we're going to do today is that we're going to talk about how to formally solve the Callan-Symanzik equation. So 3 things. Callan-Symanzik is the statement that the renormalized correlation functions are actually up to the z's. You know what I mean by this. The renormalized correlation, this statement is a little bit imprecise, right? The renormalized correlation function, once you take into account the running of the wave function, so the wave function normalization, then it would be invariant, right? In fact, all physical observables, including the S matrix, must be invariant under this transformation. Write down an object that is not invariant under the RG flow cannot be an observable. Remember when in QFT1, I said quantum field theory always comes with a coupling. That's our cutoff. The physical observables are the set of low energy observables, low energy objects that are independent of this cutoff. This is precisely the manifestation of that independence, right? Anything that is observable must be like that. So, question, is the S matrix observable? S matrix is observable. So it must be invariant under this. Therefore, there's a Callan-Symanzik equation for it. We don't call it Callan-Symanzik. This is what the equation is. How about the effective action? So this I leave for you guys to think about. The effective action, something you could observe. Is there Callan-Symanzik, or is there some sort of flow equation for the effective action? You probably know the answer to it, but any guesses? Sorry, let me say something. So things that are every physical observable must be invariant under this transformation. However, not everything that's invariant under this transformation is physically observable. Sometimes physical observable have extra criteria. For example, what examples you know? An odd point correlation function of fermions, right? Satisfies Callan-Symanzik equation, so it's invariant under this, but it's not an observable. Why? Under rotation by 2 pi, it becomes phase. Or similarly for anions. All right. So let's start with composite operators. Let me pause for questions. Questions? So this I'm done with the review of the previous lecture. So composite operators. So far we've discussed phi x, phi y. But the question is, by the way, the terminology appropriate for this is operator value distribution. Good. The reason is that, yeah, so how do you go from this to physical observables? We discussed this in QFT1, I think, right? You take a function of space-time, you integrate it against it. Now, that will make sure, if you have some smoothing, if this, in a generic interacting theory, if you integrate by some x f of x mu x mu over some region, if this f has some smoothing in time, it will immediately make the norm of this guy finite. So that's good.
That's meaning.
Huh?
That's meaning.
Smear. It has to be smear in time. In a free theory, smearing in space suffices. Free theory has this nice property. It's called time slice accident. So, but then it doesn't mean that this operator. Well, then there's a problem with this. This is an unbounded operator, right? It's a well-defined operator. So this is an operator value distribution. This is a legit operator, but it's unbounded. If you exponentiate it, you'll get bounded operator. If you do spectral analysis, then you get unbounded operator. Okay, so now can you define phi 2 of x? You would like to define it by taking this limit, but then there are short distance UV divergences, and normal ordering was the method we invented to subtract these divergences in the free theory. When we write m squared phi squared, the mass term in the Lagrangian density as a classical term, right? I've been calling it casually these terms of operators, but those are the terms we write in the path interval. To make sense of them as an operator, you have to make sense of this as an object with finite bounded fluctuations, right? And normal ordering is what makes this an operator. So as I said, like so far, I've been casually just using the terminology of calling whatever you put inside the path integral an operator. That's not necessarily an operator. Classically, it's easy to write phi of x squared, but quantum mechanically, you have to make sense of it. All right. Now, let's just think a little bit about composite operators. So let's say we use normal ordering. And by the way, one of the most important things about, one of the good things about defining quantum field theory as some deformation of a CFT, say free field theory, is that in the vicinity of a CFT, you put normal order, right? The trick that we use for normal ordering, there's a version of that for interacting theories as well, if they're a CFT. But in general, if you don't want to define quantum field theory that way, it's hard to make sense of composite operators at all, actually, unless somehow you have some other symmetry that saves you. All right, so now let's see how to make sense of the renormalized operator squared. So phi of r in renormalized perturbation theory, we define it as some z of phi of m, phi naught of x. Phi of r squared is not this object squared as we saw in normal ordering. So it deserves a brand new wave function normalization. Now, importantly, z of phi squared of m is not z of phi m squared because of anomalous dimensions. If this was an equality, we would say that that operator has no anomalous dimension, because the dimensionality of this guy is fixed by this, right? Classical analysis, just naive dimension counting, will tell you that this will have to be twice that if there were no quantum corrections, right? But because there are quantum corrections, you have anomalous dimension, and this equation doesn't hold. More generally, an arbitrary operator could be defined as a bare object, and then its renormalized thing will be related to the bare value by some operator renormalization, operator wave function renormalization. The terminology of wave function renormalization I really dislike, but unfortunately it's super standard. So Z's, there's no wave function here. You only get wave functions if you think about the one particle Hilbert space. Now there's something funny happening. Is it possible that, so far we've been writing things like this. We've been saying that, every field phi of I at scale m will have its own wave function renormalization. Phi I 0, there. Is it possible? This already assumes that as you flow towards the infrared, the fields don't mix. If you start with a theory that has a Lagrangian density of phi 1 and a Lagrangian density of phi 2 and a coupling in between them, the coupling in between them, for example, Yukawa theory, will tell you that generically you expect them to mix, things to mix. Now, for them to be mixable, there's only one rule that will forbid mixing between operators. What is that rule? Symmetry. If there's, for some reason, the objects that we're talking about, the operators that we're talking about have different charges, quantum numbers, that they cannot mix, right? There are super selection rules that will tell you they cannot mix. But generically, if you write down some OP of M, this is a sum over P prime of all the bare operators, right? With the same quantum numbers. We actually see these examples of all sorts of operators mixing with each other under our G flow. This is an important phenomenon. The rule of thumb is this: in an interacting theory, anything that is is allowed will happen. Any term that's allowed by the symmetry will happen. Every mixing that's allowed will be generated, unless it's forbidden by symmetry, right? So you should immediately realize that these equations we've been writing are a little bit simple-minded because of these possibilities, right? They're okay in the perturbation theory in the vicinity of a fixed point. Is this clear? Yeah.
Why do we expect them to mix more as we do our sheet?
Because there's more and more interactions allowed. You know, like as you, let's say you find in your theory to have like a bunch of terms. As you start flowing, you know, like there's all sorts of higher order interactions that appear, right? Because higher loops will create all sorts of external legs, right? Yeah, as you run under the RG, well, we're gonna talk about this a little bit. Even locality is naive. Locality is not preserved. But anyway, I didn't say that. It's a true statement, but we don't want to think that way. I only have one I've included only one lecture on that, and then you hear about it, you forget about it.
Locality in the usual sense we've been using it so far.
Locality, yeah. Well, we'll come back to it. Under the RG flow, in general, locality is lost as well. In general. What is special about renormalizable theories is that it's believed that you end up with some local descriptions in the thread, far away down. Anyway, we don't have to worry about those things. By the way, what is a non-local theory? One way of thinking about non-local theories is, well, let's say instead of a 5x squared, tell me a non-local version of it. Tell me a term including the, so here's a local term of interaction. What's a non-local version of it? Yeah, exactly. So 5x1, 5xn integrated with some kernel over dx1 to dxn. Now, if these guys are nearby, I can think of this as phi of x1 to the power of n plus a derivative expansion. Right? What happens is the following. As you flow under the RG, you could start with this term. RG introduces higher derivative expansions, higher and higher. And every derivative expansion allows you to become a little bit more non-local. Within perturbation theory to an arbitrary order, a perturbation theory, this truncates to the finite order. There is what this is called quasi-locality, right? But if you do this non-perturbatively, things go nuts, right? So in general, we expect things are not local. Is that clear?
Is that a consequence of the theory itself, or?
There's nothing about this theory special. Generically, higher derivative terms, the higher order terms are produced in RG. As I said, like unless a phenomenon is forbidden by symmetries, it will be generated. You always find some Feynman diagram. And if you fail to find a Feynman diagram that will contribute to a coupling to arbitrary order in perturbation theory, there's a symmetry in your theory you've missed. This is actually very important, but that's another story for another day. Good. All right, so now we could define anomalous dimensions for an arbitrary local operator. How do we define that? You take Ln of Z of O, do M del M of it, and call that the anomalous dimension. All right, so the logarithm is important here. Do you see why? Well, we'll get there. Let's work out an example. These two lines are incredibly simple, but very, very important. Imagine you want to calculate the anomalous dimension for an operator, which is phi n. As a physical operator, it's a renormalized operator, a scale m. So it's phi n of m and x. Let's make it simple. Imagine it's related to the bare thing, only it doesn't mix with anything else. It's related to it by some z of phi n, some wave function normalization for this operator. There are two steps to the RG. You send M to MB, you lower the physical scale, then you do a while transformation to make up for it. So let's do that. First, let's lower this from x to x over b. If this is deep in the UV, and deep in the UV is, this is like if the bare theory is like very, very deep in the UV, this will, the deep in the UV theory, let's say is 3 or something, this transforms with this naive dimension counting power. So it becomes b to the power minus m, the classical dimension, which is if say phi n is d minus 2 over 2 times n. Right? Deep in the UV, the theory is basically free. Right? We're assuming that we define a free theory. So this first line is this. Is this part clear? Next, what do you do? Well, what you can do is that now take this term, put it back in here, and use. Let me write it on the board. Actually, let me put it here. So phi n of x over b, z phi n of mb is phi n of mb x over b, right? This is just, I copied this equation with new values. Use this equation to eliminate phi n in here, and you get this. Good? All right. So last step, take b to be very close to 1. Right? What do you obtain? You obtain this term is the only thing that matters. And in the limit of b going to 1, this will transform as, well, sorry, there is this b to the power minus nd classical that will appear. Oh, sorry. Yeah, well, okay. Anyway, you repackage this as b to the power of gamma of phi n plus nd classical. So whatever this power is, you call it nd classical. I think there's a minus sign, overall minus sign I'm making. Yeah. This is the anomalous dimension. And if you see what the anomalous dimension is, you want to know what it is, it's literally this expression. It comes from the variation of this term with respect to b. When you vary this with respect to b, there's one term coming from here, and then there's another term from here. So the anomalous dimension is present because z of phi n over m over z of phi n dm is not transforming trivially with what you expect, right? This is, if this were z of phi m to the power of n, and if this were z of phi bm to the power of n, you would have had no anomalous dimension. So what naive power counting missed when we started our discussion of RG was that naive power counting was some sort of analysis based on the UV. It's just classical. Quantum corrections will change that, right? There is one more thing that you need to know here. Do you see now why there's ln of z here? Well, you just plug it in, do the calculation, you find that there has to be ln of z is the thing that will contribute this way. If gamma is defined this way, then you find this equation. All right, questions about anomalous dimensions. So anomalous dimension is when the dimensionality of a composite operator is different from the sum of the dimensionality, the naive dimension counting, or is different from the naive dimension counting that we associate with, which is the sum of the dimensionality of each operator individually. When the composite thing is different from the whole thing. But that makes sense, right? They're quantum corrections. As you bring operators near each other, they're quantum corrections, they interact, right? We saw that in simple examples, you know, like when you look at the correlators, as you bring them closer and closer, due to interaction, there's an effective potential between them, right? And that will change the energy or the correlator. So quantum corrections will allow for anomalous dimensions. And of course, beta functions, right? Running of the couplings. Now, one more thing. To have everything under control, not only you want beta functions to be small, but you also want the anomalous dimensions to be small, right? To have some sort of perturbative control. There are, we're gonna encounter setups where, yeah, okay. I said what I said. All right, questions. Let me pause again. So is the idea of anomalous dimension clear? Is the idea of composite operator clear? You already see hints of a structure that's called the operator product expansion. Do you see it? In normal ordering, do you see it? So consider phi x plus epsilon. All right, I'm just going to choose as if it's one dimension. So this is an operator. If I calculate the expectation value of it, what do I get? The expectation value of it is going to be something like this in the vacuum. So I can think of this operator as this times identity. Because if I calculate the expectation value of that with identity, I get that. But now there is a little bit of a problem, because as you take these guys close to each other, we saw that there is something that is not A. There is another operator there that we call phi squared. So there will be another operator here, phi squared normal order or something. In principle, as you take these guys closer, this might or might not exist. You're going to have all sorts of higher derivative expansion. So the formal structure is a formal expansion of this form that all composite operators, a bunch of functions of x minus y minus x, right, over p's. This is called the operator product expansion. It's some formal expansion this way, right? So when you take the operators, make the operators collide, right? When there is mixing between different things, those are all the things that can appear on the right hand side. So you could view this inside this operator. There's an identity, there's another thing, there are a whole bunch of things. Now in a CFTs, this is taken as the golden principle. When you don't have Lagrangians, you just have a list of OPs. Somebody gives you a list of these guys and you work with them with a bunch of properties. What are the operators here? What is a field? The operators we put here are the fields, right? The basic fields. What are they? What did we define? Like in field theory, when we wrote down Lagrangian densities, what are the things that we picked here?
Free rows.
These are irreducible representations of the Poincare group or its universal cover. Those are our fields. If you have a CFT, you start with irreducible representations of the universal cover of conformal group. You will have to run the whole analysis from scratch, right? When we wrote this, we had in mind something with a mass and a spin, because that came out of the representation theory of the Poincare group. In a CFT, the representation theory will label that with a bunch of other charges, quantum numbers, right? But the formal OP structure will survive. Okay, I'll shut up now. Good. Questions? Now, I want to spend, no, I'm going to pause for more questions. This is a change of story. Any questions about composite operators, renormalization of them, anomalous dimensions? These are very foundational concepts. So when we said that in quantum field theory, the notion of a field or particle is completely emergent, what do we mean? We gave examples of, like in the phonon theory, where you had UV degrees of freedom with very different properties than the infrared particles. So in the UV, you have your fundamental fields, right? Whole bunch of objects made out of them. As you flow, what happens is that under renormalization, all of these guys mix. Once you flow really deep in the infrared, in the phonon theory, the excitations of the phonon theory, there were actually sums, if you recall, there were Fourier transform or Bogoliubov transformations of these UV degrees of freedom. They're highly non-local rewritings of them. The fact that there's a mix of them, it tells you that under the RG, there's operator mixing, right? And then they got repackaged into new representations of a new symmetry group, right? In the infrared, the symmetry was actually relativistic. There was an approximate relativistic symmetry, if you recall, right? So that's one manifestation, one example where the infrared and UV degrees of freedom are very different. When we started saying that the degrees of freedom are like not, they could be emergent, right? The UV and IR degrees of freedom are different in QFT1. When we said those words, this is the formal aspects of it. Under RG, things mix. And in general, anything goes. All right. So I'm going to spend the remaining time of this lecture talking about, so we wrote down the Callan-Symanzik equation. We're going to now solve it. It's all you need to know is a method in PDEs, partial differential equations, called the characteristic method. It's very simple. I'm going to give an analogy following Peskin's analogy. I think it's due to Coleman, to make this very, very simple. But there are key ideas that go into it. There's physics associated with this. All right. Let's start with the simplest thing possible. We have a lambda phi 4 massless theory, scalar field theory, and we're going to look at the Callan-Symanzik for the 2-point function. All right, good. So what is Callan-Symanzik for the 2-point function? Is this equation. Good. All right. So we have renormalization conditions. We want to, the fact that we call this massless tells me that it better have this form of I over P squared, because the pole should not change. Now, the overall thing, it could get multiplied by P squared over M squared. The full M-dependent renormalized 2-point function for the normalized fields will have to take this form. The fact that it has to remain I over P squared is a statement about you don't want the pole shifted. But the residue can change, right? Because the fields are changing. So field normalization. So, but it will have to take this form of, it will have to depend on P squared over M squared. Do you know why? It's a very important comment. Well, okay. Think about why it has to be a function of P squared over M squared. It's very, very fundamental statement. You could convince yourself of it using Feynman diagrams or perturbation theory, but there's a more grand argument that will tell you that. So it's an ansatz. well, I have to make some assumptions. It's an ansatz, and then by the virtue of the fact that you would like this to represent the quantum corrections, or the running, you would like G of P squared over M squared to go to 1 at the Gaussian fixed point. Good. All right. So take this as an ansatz for the 2-point function. It satisfies this equation. Can you see it? Just take derivatives. It will satisfy this equation. Good. This equation looks, it has the flavor of Callan-Symanzik, but it's not Callan-Symanzik. For one thing, this is 2, and this is P del P. Right? But now what we can do is that we could use this equation to replace for MdM in the Callan-Symanzik equation. What am I doing? I want to solve my Callan-Symanzik equation for the 2-point function. That's a hard task. The first step of solving any PD or any physical problem of this type is that use your symmetries. Use your symmetries to write a general ansatz for the function you're trying to solve. Right? Here's what I've done. I've used my symmetries of the problem to write down the general ansatz for it. Now I plug it in. I get this relation that I can use to simplify my Callan-Symanzik. It becomes like this. All right? So at the tree level, when this correction is not there, this is minus I over P squared. Then beta is equal to gamma equal to 0. Right? It satisfies, it's pretty clear. So this is what your Callan-Symanzik equation is now. I traded M dependence for P dependence. You're with me? Good. All right. Next, let me do this half-page thing. Introduce, now there's a little bit of a weird step. Introduce a new variable t, which is log of p over m. View it this way. What you want to do is you want to write p del p as del t, right? But you can't write log of t is equal to log of p, because that's gibberish. That makes no sense. What's inside the log has to be dimensionless. So you write it as log of p over m, the only other scale in the problem. Good. So that's your del t, and then minus beta lambda del lambda, that's your beta function. Package this 2 with this gamma of lambda to write it as 2, 1 minus gamma of lambda. All right? Okay, so this is a differential equation. Can you suggest a way to solve it? I'm going to spend some time on this too. Huh? Oh, no. How do you integrate a differential equation like this? Try to use an analogy. Think of t as time, right? So if you're trying to solve a PDE of this nature, the first thing you would do is you try to get intuition from it, is to try to drop terms from it to see if you recognize it. So let's just drop the second term. So let's just look at del t minus beta lambda del lambda of g2 equals 0. A function, some g of lambda and t equals 0. You recognize this differential equation and you know the solution to it. If you don't recognize it, if you can't guess a solution, make it simpler. Imagine beta is independent of lambda. So write it as minus del lambda of g of lambda and t equals 0. You recognize it now. No.
Beta t minus.
Okay. I'm gonna make this very obvious. So call beta v, call lambda x, g of x and t equals 0. Can you solve it now? What is this equation? Really?
I mean, what is the name?
You don't see the fact that it's a wave moving with some velocity?
Yeah.
That's what the wave equation is. Right? So it's a wave that moves in this direction. Right?
Don't you need that's related?
Ah, very good point. It's not a wave equation. Sorry, I misspoke. What this is a function that's moving. So something that's moving, right? This del t of x. Well, no, let me. So it's just this is moving, right? Now the movement has position dependent velocity. So think of it as a pipe. Something is moving, and the velocity depends on the position. So Coleman uses an analogy. He says, imagine this is the density of a colony of bacteria sitting in this stream of water, right? So this part of it tells you that start with some density rho of x and t. At some later time, that will be at rho of x prime, x bar of t and t, where x bar of t and t, this is where this motion takes you, right? That's just,
Why does T have the same coefficient? T is some different.
So-
Different time steps?
say it again.
Are you taking different time steps, like after a time?
No. So at some, let's say this is 0. I realize. Oh, sorry. Yes. Good. So the analogy is that this is like a colony of bacteria, and then what's happening is they're sitting on some stream. The colony of bacteria, the density of them is a function of position and time, and this is just flowing, right? And the flow is given by has velocity v, that's position dependent. Now, turn it around. What is lambda? What is x? It's lambda. So you have a 2-point function, which is a function of t is scale, normalization scale, and lambda is a coupling, right? So as you change the scale, right, as you add the velocity, the running of the coupling depends on one coupling what you are at, right? You got this part? All right. So it's a fluid with a particular velocity v going down the pipe. All right. Now we're gonna add the other term. But before adding the other term, let's do a different way of doing it. So let's drop the beta term now and only focus on the f term. Plus f of lambda of g2 is 0. Okay. Good. Can you solve this? That should be easy, right? This just grows by this power. Right? It's just some growth with some power. So what does it mean? Imagine in your previous equation, there's a colony of bacteria that's moving down the stream with some velocity dependent. Now set v equals 0. So there's no stream. This part tells you that the colony keeps splitting and it grows. The density grows, right? And the growth is the function of the location, because lambda was x, right? At different places, it grows at different rates. Now, what happens once you put the two equations together? This velocity things becomes the rest frame of these colony, right? At the rest frame of the colony, velocity is 0, so the colony is just expanding, spreading with the rate that's allowed by the position. Now, you add to it the fact that the position is moving, and that's your full solution. All right, so what does it look like? So the density of bacteria at point x at time t is d of x and t. as you move along the fluid, it just goes to x minus vt of x minus vt of 0 goes to xt. These two are the same, right? So this is what this is a solution to that when its velocity is position dependent. Okay, so this is solving for the position as a function of t and x, right? This is the beta function. Now, in our analogy, this is telling you that write down the so what's the right hand? This is a beta function. So you're solving for what is d of ddt of the coupling with respect to the beta function, right? So you're integrating the beta function equation. You're imagining beta function. You know, your beta function is the variation of the coupling as a function of scale. So you integrate, go to lower scale, right? And then at that scale, you find what the coupling is. Starting with some initial coupling x at some scale, I'm calling it schematically 0, right? You flow, and at some lower scale, you end up with coupling. Lower scale t, you end up with some coupling. This was your initial point. Good. So this is this part. That's moving. So solving the beta function, integrating the beta function equation, the running of the coupling gives you this colony of the bacteria moving down the stream. Now, what is the role of the anomalous dimension? It's about how the operators grow at different points. Different points means different lambdas. At different lambdas, operators grow at different rates, right? So as you go down as you change the scale, the coupling grows. At some later scale t, the coupling is lambda bar, and this is the initial coupling. Now, at that point, along the way, at any point you are, the growth rate is given by the anomalous dimension, right? So here's the full answer. So d of the colony of the bacteria at position t and x is the colony of the density of the density, initial density at the location that you integrate, where it would be, and this is telling you about how much it grows, right? From 0 to t, this is the rate that it grows at. It's only dependent on the position, but this is where the position is. So in summary, you could write it this way as well, and I want you to think about why. But in summary, here's the analogy. T is log of Q over M. Lambda is X. Beta is the minus beta's velocity. The anomalous dimension, 2 times anomalous dimension minus 1 is the, so I call this rho. I shouldn't have called this rho. Call the density of bacteria D, and rho is the spreading rate, right? And the density of bacteria is a 2-point function. The solution looks like this. You take the 2-point function that you had in the UV as a function of lambda. You plug in the lower energy lambda, right? Lambda you would obtain by flowing to the particular energy under the RG. But now you have to take into account that the operators grow as you flow. And this will tell you how much they grow, right? This form of the equation, this is that integrating the velocity equation, right? This form makes beautifully splits the two phenomena, right? It gives you some sort of intuitive intuition. Under the RG, the operators grow, right? And their wave function, there's wave function normalization, but the couplings run as well, right? Remember when we wrote, we had G of N of M, and so M here becomes, what do we call it? T, I guess. It will be related to T, right? And then beta, not beta, sorry. Lambda of M, I guess lambda of T. It will be lambda bar of T, right? And then there is a wave function normalization. this part of it has to do with the first part. And then this part of it, which is the wave function normalization, has to do with the growth. Right? So the equations are very easy to integrate conceptually. Now I did this for 2-point function, and you're gonna do this for like higher point functions and other examples in your homework, but I can't stress this enough. This was successful because I started with a good ansatz for my endpoint function. If you don't take a nice ansatz, you haven't used your symmetries, you're gonna get very difficult things. It will be very difficult to solve, right? Structurally, this is the form of the endpoint function, right? The contribution of z comes from that bit, and then z will depend on the new coupling at lower energies. All right, questions? All right. Yeah, I have to. I want to make sure I finish this story. All right. So what did we do? We introduced this composite operators. We talked about how we could associate wave function normalization or anomalous dimensions to them. So in general, if you take a bunch of composite operators and deform your Lagrangian density this way, some fixed point this way, an example of this was an m squared 5 squared term. These CIs are in principle dimension full. So I'm no longer talking about the renormalizable theory where the couplings are all, the coupling is dimensionless, right? So the principle of Callan-Symanzik is exactly the same still. So you have MDM plus sum over I gamma I. Now you have MDDM of del CI, del CI of GN. But now this CI is dimension full, right? The way to deal with it is to take out the dimensionality of it. It will go like m to the power of d minus delta I, right? Delta I is the dimensionality of this guy. Why? Because this should integrate it against d, should have the Lagrangian density. Should be action, sorry, I think this is, I wrote this poorly. Good. All right, so the principle is simple. You basically write this and separate the dimensionality from you write everything in terms of dimensionless coupling, take out the dimensionality explicitly and put it out there. Now, what happens is, well, just plug it in there. You have to have MDDM, CI is this guy, right? That will give you gamma, this has to, yeah, okay, sorry. This has to be gamma ICI, right? Because I'm calling this gamma ICI. That's what we call the gammas for an arbitrary composite operator. So once you massage this, you could write it this way as a function of rho I, ddt, dt is still that old dt of ln of rho I of t is gamma I minus t plus delta I. Just like there's one line of algebra from this to this. Plugging that inside the Callan-Symanzik, you find that the endpoint function of these composite operators. So what am I doing? I'm calculating now the endpoint function, the Callan-Symanzik for endpoint functions of composite operators, right? It will look like this. There will be MDDM, del I gamma I. These are the wave function normalizations. And now these are the related to the beta functions, right? This question? Or? Okay. But the idea is that you write everything in terms of dimensionless couplings. The flow of the dimensionless coupling is given by beta of that, right? Which is minus d plus delta I plus gamma of I, rho I. Now, if you look at the coupling, you could integrate it. Integrate the beta function for this. What do you find? You find that, you remember the Callan-Symanzik equation, there was a part that the wave function grows, but let's just think about the part that's like where the coupling ends up. The coupling, if you integrate it, ends up at the initial coupling, m over p to the power of this. Good. Imagine gamma I, these are quantum corrections, right? Imagine gamma I is 0. If delta I is less than d, right? That means that the coupling decays in the infrared. Sorry, grows in the infrared. Oh yeah, I'm changing the p. Wait a second. I'll see positive. Yeah, I'm lowering the p. Anyway, I got confused. But anyway, this is the structure. This is when you integrate it. This is the coupling, where the coupling comes out. The point is that if the dimensionality of it is positive, like mass squared, it grows. All right. An example. Phi squared, mass squared, right? This is how rho of m bar is rho of m, m2 over p2. So this is what it looks like, and this is the oh, sorry. You end up with small corrections. Now imagine we flow from a UV fixed point to an infrared fixed point. We're going to see that in the next lecture. Well, we saw that very briefly before. This is a Wilson-Fisher fixed point. What's going to happen is that this mass term, this phi squared, is going to become scaling operator of the IR as well. And there will be some not so small anomalous dimension. We're going to see that. This is my last slide. All right. Good. Now, let me see. I don't want to say this. This is the solution to the two-point function RG flow. Imagine as I said, we flow from a UV fixed point to an infrared fixed point. So at the infrared fixed point, the coupling associated to this becomes some new coupling. At the fixed point, the value of the coupling change becomes lambda star, right? If you evaluate this at lambda equal lambda star, in the low energy theory, you expect it to behave like 1 over x to the power of d minus 2 with this anomalous thing. Let's stir this. Now, the very fact that there's log of x over m in the exponent tells you that when you exponentiate, that could be repackaged as 1 over x to the power of d minus 2 plus 2 gamma on the star. So you end up with a scaling field in a CFT. This is a two-point function of a CFT, right? With some critical exponent, anomalous scaling dimension. We'll discuss this example in more detail next time in Wilson-Fisher. It's a Wilson-Fisher fixed point. All right. Any questions? It's the end of this lecture. So what did we do? We defined composite operators in the vicinity of a fixed point. Well, or at least we structurally talked about them. We talked about the Callan-Symanzik equation for it. We talked about Callan-Symanzik for endpoint functions of composite operator. And then we discussed what the structure, how would you go about solving the Callan-Symanzik equation, the structure of it, using this analogy of, well, we integrated the G2 explicitly. You're going to do the G4 example. But the structure is there's a growth of the wave function that depends on lambda. And then there's the lambda that changes the function of scale. Yeah.
You know that the wave function here decays with a power law instead of exponential. Does it have something to say in regards with entanglement?
Of course it does, but that's the fact that it's power law is just it's a CFT requirement. The two-point function of a CFT must be a power law. Why?
Because of scaling length.
Because of scale invariance, right? It's the only thing you can write down. They have no other scales. To write down an exponent, you would like to write exponent. Whatever you write in the exponent has to be dimensionless, right? So you have x. You don't have any masses. construct anything dimensionless out of it. So it must be like this. It is important that this comes out as logs. The logs are important because the logs are the things that when you exponentiate result in an anomalous dimension shift. This issue of logs has been appearing over and over again, right? All right. Any last questions? No, thank you. I haven't posted homework 3 yet, but I will do that tomorrow.
There's no rush, no worries.